Okay. So let us quickly recapitulate what we studied. Let's say we have a partial order denoted by this. So let us draw an example partial order. Let's take a simple order. So I am drawing what is called a C diagram. Let's number the elements of the partial order set. Okay, let us quickly. I hope I'm audible. Just anybody confirm if I'm audible and visible.
Yes, sir.
Thank you. Okay, so let us quickly do some definitions. So greatest element is one element such that all x in P, or the element, let's call it as G or something, is all elements of P are less than equal G. And I'm not writing the equivalent, so there is an equivalent list element. So in this partial order set, this is the greatest element, and similarly this is the least element. Okay. Note that it's possible that there is no greatest element in a partial order set. Say for example, take this partial order set. There is no greatest element, neither there is any least element. So this is greater than this, but this is not comparable to this. So I cannot say that this is greater than this. But it should be greater than everything, every element of the POS. Similarly, this is not a greatest element, this is not a least element, this is not a least element either. But one thing is clear: if there is a greatest element or a least element, it has to be unique. There cannot be multiple greatest element or multiple least element. So if unique, if it exists. Okay, this is an important point. If it exists, by definition, it has to be unique because it is greater than equal to for all x. Okay, so there is another concept. Let us see. It is called the upper bound and lower bound. Upper bound and lower bound. Let me quickly draw a diagram. Okay, so it's again defined for a partial order set, but you take any subset of the partial order set. Let's say I take this subset. Okay, so the upper bound of S would be that set X such that X belongs to P, so all elements in P, and X is or this is not the right symbol. So for any for all A in S, A is less than equal to X. Okay, so one element belonging to P would be called an upper bound of the subset S if it is greater than equal to all elements of S. So if this is my S and this entire thing is my P, then you see this is an upper bound because this is greater than this, and this. Similarly, this is an upper bound. This is greater than this, and this. This is upper bound. So the set upper bound for this would be, for S would be this set. Similarly, you can define for lower bound. Least upper bound. Least upper bound. Okay, so some element x is a least upper bound of S if and only if x belongs to the x belongs to the upper bound of S. So this belongs to the you take the upper bound, take the set upper bound, and x is less than equal to y such that y is a member of upper bound of S. So you take the upper bound, and one of the element of the upper bound would be called a least upper bound if it is less than equal to all members of the upper bound. All members of the upper bound. For example, this is a least upper bound. So this is the upper bound of S, and this is the least upper bound of S. Why it is the least upper bound of S? Because it belongs to the upper bound and it is less than equal to all entries. It is less than equal to this, it is less than equal to this, it is less than equal to itself. So it is less than equal to all elements of the upper bound. Then we call it as the least upper bound. Similarly, you can have the greatest lower bound or GLB. Note again that if a least upper bound exists, it has to be unique. So LUBS is unique if it exists. Okay, it may not exist also. It is possible that it may not exist. Okay, but if it exists, that then it has to be unique. Okay, for example, let's take this case, this kind of a POS. Okay, so if this is your S, then this is the entire upper bound set, and none of these are the least upper bound. This is not a least upper bound, this is not a least upper bound, this is not a least upper bound. So there is no least upper bound in this case. So if they exist, it is unique, but it may not exist. All right. So now we take a particular case of the least upper bound. Okay. You take a particular case, least upper bound of A. So I said before that least upper bound can be defined for any subset of the partial order set. Okay. Now let us consider sets which are pairs of elements. Pairs of elements. Okay. So least upper bound of a pair of element. Let's take an example. Let's take this again. Or let's take maybe this as an example. Okay, so now my S, my subset is only pair, only two elements at a time. So you consider least upper bound of a pair of element. Let me number them A, B, C, and D. So I would talk about least upper bound of only pairs. Let's say the pair AB. Only pairs. And similarly, greatest lower bound also of only pairs. Okay, so what if I take this pair, let's say this and this, let's say I take this set. What is the least upper bound? Least upper bound is this. This is the least upper bound. And what is the greatest lower bound? Greatest lower bound is this. Let's take something here, A, B, C, and D. So I take A and B, A and B. What is the least upper bound? Least upper bound is this. What is the greatest lower bound? Greatest lower bound is this. Let's take A and C. Let's take A and C. So this and this is my set. So what is the least upper bound is this. Greatest lower bound is this. So I define for pair of elements. In fact, what I do, the least upper bound and the greatest lower bound for pair of elements, I give them a name. I give them a name. I call them as join and a meet. Maybe I'm confusing this. I have to check up. I'll check up the slides. I often confuse between these two. So a join and a meet. So I call least upper bound of a pair of elements as a join. I may be wrong. I'll check out the slides. Maybe the name is the opposite. And the greatest, anybody can correct me. Is this the right name I'm giving? Anybody? Do you want to correct me? Okay, anyway, nobody is correcting me, so I have to check the slides. Okay, whatever. The idea doesn't matter what's in a name. So the least upper bound for pair of elements, similarly the greatest lower bound for the pair of element, I give them a name. I call it as the join and the meet. In fact, there is another name for this. This is sometimes called a product, and this is sometimes called a sum. Okay, but note that the least upper bound and the greatest lower bound, they are themselves elements. They have to be elements of the partial order set P. And I write them as symbols. So this is denoted by this symbol, and this is denoted by this symbol, or product as this symbol, and sum as this symbol. Sometimes there is a symbol. So instead of this LUB and all this, I would write them as this, as the join, and this as the meet.
Excuse me, sir.
Sir,
the symbol should be exchanged.
Symbol should be exchanged. Yes, symbol should be exchanged. Yes, correct. You are correct. In fact, there is a nice way to the way to represent them. We'll see that. Okay, so this is the join, and this is sometimes denoted by the sum. So this also should be exchanged. No, let me see anyway. So this is represented by dot. Okay, so this is the least upper bound. So this is the least upper bound. This is least upper bound is this, and this is the least lower bound. Again, you see, because of the property that LUB and GLB for any set has to be unique if it exists, the join or meet for a pair of element are also unique if they exist. It is possible that they do not exist, but if they exist, they are to be unique, both join and meet. Okay, so I can think of these join and meet as kind of binary operations. They take two elements, produce a third element. The third element is either a least upper bound or a greatest lower bound for a pair of elements. Okay, so I can think of the join and meet as algebraic operators, as operators. Okay, and there is a closure property in the sense that if A and B are elements of P, A join B will be an element of P, A meet will be element of P. So there is a closure property. Okay, so I have now defined join and meet. Let's quickly see what kind of so just a kind of pictorial representation. So if you take a chain, A, B, C, and D. So if you take any two elements, let's say take this and this, they are least upper bound would be the one of them. So one of them. So if you take say B and B, B join D. I really have to remove this confusion about the name. But anyway, B and D, it's D itself. Similarly, you take this, it's B itself. Okay, so if it's a chain, the join and the meet of two elements in either case are one of the elements. Okay, and note one thing, that if two elements, a pair of element that I'm talking about, if they belong to a chain, always there is an unique join and always there is a unique chain. Unique meet. Now let us look at this kind of structure. One property about the chain is that it's a total order, in the sense that every pair of elements are comparable. Every pair of elements are comparable, and if they are comparable, this will definitely, join and meet will definitely exist. Let us look at a structure like this, where every pair of elements are not comparable. Every pair of elements are not comparable. Okay, say a diamond kind of structure. So here you see, here also it is defined. It is defined in the sense that the upper bound of least upper bound of A and B is this, and the greatest lower bound is this. So they also exist. What about something like this? What about something like this? Does every pair of element have an meet and a join? Can anybody say every pair of element? Okay, so if the elements in a chain, I know all of them will have a unique meet and a join. What about elements which are not comparable? For example, what about A and C? What about A and C? What is the greatest lower bound of A and C? Anybody?
So
What is
B.
the B? Similarly, the greatest least upper bound of A and C is E. And similarly for A and D also. So every pair of elements you see in this structure has a meet and a join. So now we come to our definition. Now we have come to our definition that a lattice is a partial order set, a set equipped with an less than equal to relation, is a partial order set where every pair of elements have a meet and a join. Okay, so in these three examples, every pair of element has a meet and a join. Every pair. So if that is so, then I call this partial order set a lattice. Okay, so I have been long time for the recap, but anyway, let us come back to our slides. Yes. So here is the definition. You can quickly check for each of these cases that condition is satisfied. That means every pair of element has a meet or join or not, and depending on, they will be either a lattice or not a lattice. Okay, so now let us look. So now from now onwards, we'll look at this meet and join as kind of binary operators, algebraic operators. Now let us look at some properties. First, let us look at the basic ordering properties of meet and join. So you think of like this. So X meet is an element of lattice. X join X meet Y is an element of the lattice. X join Y is also element of the lattice. So are they comparable? Are there some ordering relation between them? We see that by definition, actually, that the meet is wait, let me correct the definition. Okay, so this is the meet. Meet is the greatest lower bound, and join is the least upper bound. At least I have, you don't forget the definition. Okay, so the meet is less than equal the elements themselves, both the elements themselves, and is less than equal to the join. The meet is less than equal to xi, less than equal to join. And if x is less than equal to y, if x and y are comparable, then the meet is the lower element. Again, if x and y is comparable, the join is the upper element. So this we have already shown, and these are basically by definition. This is important. This is the transitivity property. That means if x is less than y, then x meet z is less than equal x y meet z. Okay, and similarly x join z is also less than equal to y join z. Now, this is not the transitive, this is the kind of absorption property. So similarly, this is a transitive property. If x is less than equal to y and z is less than equal to w, then x meet z is less than equal to y meet w. This actually is easy to prove. This actually is easy to prove. Okay, this I think is the proof for this. Yes, this is the proof for this. This is actually easy to see. This is this fourth bullet point that we are proving. Okay, so denote the meet by v and the meet of x and j by v and y and j by u. Okay, so because of this ordering property, v is less than v is a lower bound for y and j, and by definition of the meet, v is a lower bound for u because v is the maximum among all lower bound. Okay, so you just see this picture. See, this is u and v. This is u and v because v by definition is the join of x and z. U is the join of y and z. So what I am trying to prove is that v is less than equal to u. I'm trying to prove is that v is less than equal to u. So let's take like this. So v by definition is less than x and z. U by definition is less than y and z. And since x is less than y, this because see this is this dashed line is an inferred less than equal to, is an implied less than equal to. Okay, so v is kind of the join of x and u, so this has to be there. This has to be less than u. So it is easy to prove that. So all these, in fact, these are pretty intuitive. I mean, if you just look at them and you just simply apply the definition of meet and join and simple transitivity, you will get this. There are some other properties that hold. Some other properties that hold. The first property is commutativity. That means x meet y is same as y meet x. Similarly, x join y is same as y join x. This again is obvious. This I am not proving. This by the definition of meet and join, these are obvious. So this is some property. You take any two elements in a lattice, they'll always hold. They always hold. And this property has important implications because when we actually define our Boolean algebra, we will see that this property, since they are lattices themselves, these properties will also be there. Let us look at this absorption property. Let us look at this absorption property. This is also important. Okay. So what this says is that if you take the join of x and y, and with that element, if you meet x, you will get back x. And if we one more thing you will notice that in all these so-called theorems that we have, if you interchange the meet and join, you get one from the other. So there is a duality by interchanging meet and join. You will get the same thing. You can observe that. So that also holds. Okay. So let us look at absorption. What does it mean? Let's quickly maybe absorption and idempotence. Let us quickly draw a diagram. I think that will be better. Okay. E. Okay. So what is the thing? Say A is A. Okay, let us take this A and B. So what is A greatest lower bound with B is C. This is C. And what is the least upper bound of A and C? A and C, it is this itself. So I get back A. I can say the same thing about join also. The dual also of this. So what is the upper bound of A and B is D. This is D. And what is the join of A and D? A and D, it's A itself. It's A itself. So this is also equal to A. Okay, so I get this. Now let us, yeah, there is a call. Yeah, sorry. Am I audible? Am I audible now? Sorry to keep you waiting.
Yes, sir, you're audible.
Yes,
Yeah,
sir.
thank you. Great. Okay, so let me come back to the slides. I lost my internet. Yes, so quickly, let us now go a bit quickly. So these are some properties which hold for any lattice. The commutativity property, the absorption property. This is important. This is useful very much. So the absorption property, I don't know, I have explained or not. Are you was that audible or not? So x, if you take the meet with join of x and y, you get back x and the dual of that. So what it basically means is that, let me come out of this. Yeah, let me try to.
Sir, sorry to interrupt. Can you please share your screen?
Oh, I forgot to share my screen. Okay, I'll do that. Is it yeah, now visible now?
Yes, sir.
Yeah, thank you. Sorry to keep you waiting. Anyway, it was, I could not do anything. Okay, so I'll write down some properties of the lattice. So you take A, B, C, and D. Let's take a simple. I'm first explaining. I can, of course, give the proof. Okay. Similarly, I can have the other way around also, dual also. Okay, so let's take this. So what is A join B? This is C. So this is C, and that with A gives me back A. So this is A. And this actually you can check for any pair. If you take any pair of elements in a lattice, this will hold. For example, let's take for A and D. Okay, so A join D is A itself, and A meet A is A itself. So you take any pair of element, this will be there, and you can prove for this also. Similarly, there is an idempotence. Which is A join A is A meet A is A. This again, I think straight away follows from the definition. So this also holds. Now there is another important property which holds is associativity. The reason I'm spending time on this is that these are, we'll later see that the Boolean algebra, which you used in your logic and other cases, is actually a lattice having some particular properties. And this, you know, are the kind of usual properties of Boolean algebra. So what we are trying to say is that these are actually lattice properties that holds for Boolean algebra. And the dual also. Okay, if you just interchange the meet and the join, you get the same. You also get another theorem. The same theorem holds by interchanging meet and join. Okay, let's see this. So what is A, B? This is C, and C join C is C itself. So this entire thing is C. Similarly, what is B and C? B and C is C itself. So this is C. And A and C is C itself. So this is C and C. So this is also C. So this is verified. Okay, I'm just hand waving. I'm not giving a proof. I'm just hand waving. I'm just explaining with an example. But you can prove this. You can easily prove this. This is the proof actually, and don't know I have time to go through this because anyway I give it as an exercise. You just go through this proof. You go through this proof. Absorption is actually easy to prove. Okay, so now these all these are actually easy to prove. Okay, so now let us so these properties, this ordering of the thing, the idempotency, the associativity, the commutativity, this holds for all lattices. But there are some special properties which holds only for some of the lattices. One of the properties is that if the lattice has a greatest and a least element, we have seen before that we can actually have a lattice without any greatest or least element. For example, this is a lattice. This is a lattice. Yeah. Let me give an example of a lattice without a greatest and least element. So this is a lattice which doesn't have a greatest or least element. Okay, so a lattice is called bounded if it has both greatest and least elements. Then we call it a bounded lattice. Usually the greatest element is given a symbol 1 and the least element is given a symbol 0. It's just a symbol, no other implications. It's just given a symbol 0 and 1. It can be shown easily again that every finite lattice is bounded. Infinite lattices are not bounded. For example, if you take the set of all integers and the usual arithmetic less than equal to operation is the partial ordering, then it's not bounded because it's an infinite. You can easily check that you cannot define a maxima or a minima. But you can easily show that all finite lattices are bounded. They do have a maxima, they do have a minima. There is another property that is important. Okay, for bounded lattices, some identities hold. For example, you take the least element and you take the join with the least element, you get back the least element. So this holds, and similarly this holds. So this max and minima are some these are important properties. So if you take the join with the mean, you get back the element commutatively, and if you meet with the max, again you get back the element. Similarly, if you join with the if you meet with the least element, you get the least element. If you meet with the largest element, you get the largest element. So these are again pretty important properties from the Boolean algebra point of view. Again, I think all this you can easily. So this is 1, this is 0. You can easily verify these properties. You take any element, you can easily verify these properties. Okay, and just by applying the definition of meet and join. Okay, so now another important property. Another important property is called the distributive property. So the meet distributes join. Similarly, join distributes meet. That means if you first take the join of y and j and the result if you meet with x, it's same as if you meet x with y and join this thing with the meet of x and z and the dual also. Okay, so if this property need not hold for all lattices, and this should hold for every pair of elements. For every pair of element, if this holds, this is the simple distributed property. Okay, simple distributed property. For every pair of elements, if it holds, we call that lattice a distributive lattice. Note, see here that in this particular example, this distributive property does not hold. This distributive property does not hold. So this is the left hand side. Let's take x as A, y and z as B and C. Let's take the left hand side of this. So A meet join of B and C is A. You can easily check from here. So, but the right hand side, A meet B and join with A meet C is B. a different element. So this left and right hand side of these are not true. So this lattice, at least for these three elements A, B, and C, we have shown for distributive lattices, any three elements has to satisfy this distributive property. Let's take another lattice. Let's take this power set, this set containment, this lattice, a cube kind of lattice. You see, this satisfies distributive. You can verify it as an exercise. You take any three elements, the meet and join will distribute themselves. You can easily check that. Okay, so this cube kind of lattices, they are distributed lattices. If you take a ladder kind of lattice, they are also distributed. But this lattice is not distributed. In fact, it's difficult to construct a distributive lattice with few elements. There are, I think, only 3 known non-distributive 4-element lattices, 5-element lattices. There are only few. If you take small lattices, it's difficult to construct example of non-distributive lattices. Okay, so this is the hypercube. This is the power set, which is the distributive lattice. Okay, now let's take a complement. So 2 elements X and Z are complement of each other if X meets Z is 0, the least element, and X join, again I think I'm confusing the definition anyway, these symbols are better for me. Similarly, X join Z is the maximum, the largest element, the greatest element. Okay, then X and Z, both of these has to hold. Only one, if one of them holds, then you cannot call them a complement. If they are complement, then, so basically it means that if, so X product X prime, if we denote Z as X prime, the complement, X product X prime is 0, X or X plus X sum X prime is 1. This just means that. If that holds, but this 0 and 1, they need not be in our discussion so far. This may be any general greatest element and least element. If these 2 holds, then 2 elements are complement. A lattice is called a complemented lattice if every element has a complement. If every element has a complement, okay, then we'd call it a complemented lattice. So even if one element doesn't have a complement, we cannot call it a complemented lattice. Let's take this. So this chain, let's say, what are the complements? What is the complement of A? So what is the complement of A? So you see that also one more thing you see that one element might have multiple complements. No, I think they are unique. They will be, for bounded lattice, they will be unique. Okay, so let's take what is the complement of A. Let's take this example rather. Okay, you see A and B are complements. Because A join B is 0, 1. They are complements.
Sir, A join B will be 1.
Or will be 1. Okay, yes, I'm again making this mistake. Good, you are not making the mistake. All right, so the A and B are complements. So usually what happens is that let's take this lattice. Let's take this cube, the power set where the less than equal to is the subset relation. Let's take this. the cube kind of structure. Can anybody say what is the complement of this element? What is the complement of this element? This is my 0 and this is my 1. So what is the complement of this element? Anybody?
So can you label the corners?
Okay, let me label the, yeah, of course. 0 and 1 I'm not labeling, A, B, C, D, E, and F. What is the complement? What is D complement?
C and F.
C.
Yes, C.
And similarly, A's complement is F. So you see the diagonal elements, they are complement of each other. The diagonal elements, they are complement of each other. Right. I think some of you can guess. If I take a 3-bit binary number, I can represent it as corners of a cube. And the usual binary complement that we defined, and if we label the corners of the cube by 0, 0, 0, 1, 1 like that, you will see they will be complement of each other. Okay, I mean just for intuition, but this is abstract algebra, so let's not take examples. You cannot take examples in abstract algebra. You have to prove. Okay. Okay, so this so you can actually take examples of lattices which do not have complement, where every pair of every element does not have a complement. You can actually give examples of lattices where every element does not have a complement. The chain will always have a complement. Similarly, this kind of cube will always have a complement. Okay, so now let us come to our final definition that we arrive at after all these properties. It's called a Boolean lattice. A Boolean lattice is a bounded, that means it has a max and min element, complemented, that means every element has a complement, distributive, that means the distributive property holds for any 3 elements in the lattice. Then we call that lattice a Boolean lattice. The extreme elements are called 1 and 0. Distributivity holds. So it's a special type of lattice. Distributivity does not hold for all lattices. Every element has a complement. It's a complemented lattice. And actually, it can be proved that if these 3 holds, if it is bounded, complemented, and distributive, the De Morgan's law holds. You can prove the De Morgan's law. You can prove the De Morgan's law. Okay. So since it is bound, so I can define my Boolean lattice as this tuple. It is a set A equipped with a partial order relation less than equal to, equipped with a boundaries, equipped with max and min elements 0 and 1, and equipped with the complement relation. This distributivity and De Morgan, they can be exchanged. That means if you assume distributivity, De Morgan's can be proved. If you assume De Morgan holds, distributivity can be proved. So you can, any one of them is sufficient. Okay, so let's take the distributivity. Then this together would be defining what is a Boolean lattice. So it's a special type of lattice which has boundary elements, which has complement for every element, which is distributive. And De Morgan's law follows from that. So this is this Boolean lattice. What we'll do next is that, so this view is kind of a set theoretic view of everything. It's set and then a partial order relations among them, and everything is defined from that, max, mean, whatever, the meet and join, everything is defined from that. So we define a algebraic structure, so to say, a lattice structure or a ordering structure, so to say. The same thing can be expressed as an algebra. Algebra means you have variables and you have operators and you have constants. So constants are the max and min, variables are elements of the set, and the operators are the meet and join operators. The duality comes that you can actually, so in the ordering or the set theoretic, I have explained everything in terms of this partial order. I can do the reverse. I can, instead of defining the partial order, I can define the meet and the join as my basic elements and my basic operations. And using meet and join, I can define my partial order. I can define. I leave it to you as an exercise again. It's very interesting. Using just, if you define meet and join exist, you can define all this partial order. So there's the another view of this kind of Boolean lattice. It's the algebraic view, and then we call it as a Boolean algebra. So in the next class, I'll stop here today. We'll next class we'll move into. So this is the proof of the De Morgan's law. So you go through the slides and go through the proofs. Okay, so we'll in the next class what we'll do, we'll examine the structure of this Boolean lattice. We'll stick to Boolean lattice definition for some more time. We will stick to the structure of Boolean lattice. We'll look at certain important characteristics of this structure, and from that we'll define our algebra. Okay, so thank you. In the next class we'll continue with this. Thank you very much.